Welcome to a video on partial implicit differentiation. We just learned in the previous video that if we have an implicit equation, we can rewrite it in the form of f of xy equals 0 and then determine dy dx using partial derivatives. And we actually showed where this formula comes from. And we can expand this to help us determine partial derivatives of functions in terms of two variables. If we have an equation f of x, y, z equals 0, which defines z implicitly as a differentiable function of x and y, then the partial derivative of z with respect to x is equal to the opposite of the partial derivative of f with respect to x divided by the partial derivative of f with respect to z, and the partial derivative of z with respect to y is equal to the opposite of the partial derivative of f with respect to y divided by the partial derivative of f with respect to z, as long as fz does not equal 0. We're not going to show where this formula comes from in this video, but we are going to look at several examples. Notice this equation is already in the correct form, so we can let f of x, y, z equal the given equation. Let's go ahead and determine the partial of z with respect to x. So we're going to have the opposite. Our denominator is going to be the partial of f with respect to z. Let's start with that. So we're treating x and y as constants. So this would be 0, 0, 0. This would be 2z. Now the reason I wanted to mention that is because the partial derivative of z with respect to y has the same denominator. And now the numerator here is going to be the partial of f with respect to x. So here we'll have 3x squared. This would be plus 3y squared. This would be 0, and this would be 0. And this fraction does not simplify, so we're done here. Now let's take a look at the partial of z with respect to y. The numerator is the partial of f with respect to y. So we'll treat x and z as constants. This would be 0. This would be 6xy. This would be minus 4y. And this would be 0. Now this fraction here does simplify. It has a common factor of 2. So the partial of z with respect to y, if we factored out the 2, we'd have negative, this would be 3xy minus 2y all over z. Let's go and take a look at another example. Again, notice this equation is already set equal to 0, so we can say that big F of x, y, z is equal to the equation in this form. Let's go ahead and start to determine our partial derivatives. Partial of z with respects to x and the partial of z with respects to y. We'll go ahead and start with the partial of f with respects to z because notice it occurs in both denominators. So we're treating x and y as constants. So we'd have 0 here, 0 here. This would be 2z. This would be 0. This would be minus 4y. The derivative here would be plus 6x. And again, the denominator would be the same here. Now the numerator for the partial of z with respect to x is going to be the partial of f with respect to x. So we'll have 2x, 0, 0. This would be 2y. This would be 0. This would be plus 6z. And now for the partial of z with respects to y, our numerator is the partial of f with respects to y. So treating x and z as constants, we'd have 0. Here we have 2y. Here we'd have 0. Here we'd have 2x. Here we'd have minus 4z. And this would be 0. So now we do have our partial derivatives. However, notice that there's a common factor of 2 between the numerator and denominator here as well as here. So we do need to simplify this. If we factor out a 2 from both the top and the bottom, we would have x plus y plus 3z all over z minus 2y plus 3x. Now be careful here. It may be tempting to try to simplify the variables, but remember we can't simplify across addition or subtraction. Let's go ahead and factor out the 2 here. So we'd have y plus x minus 2z. Our denominator is going to be z minus 2y plus 3x. Let's go and take a look at one that has some trig functions in it. So we'll have the partial of z with respects to x and the partial of z with respects to y. Now notice here the equation is not set equal to 0, so let's go ahead and rewrite this in the proper form. We'd have f of x, y, z be equal to sine x, y plus sine y, z plus sine zx minus 2 equals 0. Now if we forgot to do this, it probably wouldn't affect your answer because the derivative of 2 is going to be 0 anyway, but we should rewrite it in the correct form. Now let's go ahead and start with our denominators. We're going to find the partial of f with respects to z, treating x and y as constants. So this derivative would be 0. Derivative of sine yz is going to be cosine yz times the derivative of yz with respect to z. That's going to give us y. I'll go ahead and put the y in the front, plus the derivative of sine zx, so we're going to have plus cosine zx. Again, we're going to find the derivative with respect to z, so the derivative of zx would give us x, so we'll write the x up here. The derivative of 2 would be 0. And again, our denominators are the same, so we have y cosine yz plus x cosine zx. Now we have two more partial derivatives to determine. Going back up to the partial of z with respects to x, our numerator is going to be the partial of f with respects to x. So the derivative of sine xy is going to be cosine xy times the derivative of xy with respects to x. That's going to give us y. So times y, I'll put it in the front. The derivative of sine yz is going to be 0. The derivative of sine zx is going to be cosine zx times z. So I'll put the z in the front. Now it may be tempting to simplify this, but remember we cannot simplify across addition or subtraction, and the arguments of these cosines are different. So we'll finish off by finding the numerator of the partial of z with respects to y, which will come from the partial of f with respects to y. So here we're going to have cosine xy times x, or x cosine xy, plus the derivative of this term is going to be cosine yz times z, or z cosine yz. The derivative of this would be 0 with respects to y, and this would be 0 as well. And again, this does not simplify, so again we found both first order partial derivatives of implicit equations. I hope you found these examples helpful.